Today we're going to create the entire universe from the equations of a theory of everything known as binary mechanics. Binary mechanics was developed from antiquated 20th century quantum mechanics by adding the postulates of full quantization of energy, space, and time. Results from the old quantum mechanics could only give a probability for a physical event, obtained from a complex number shown here. We can parse the items of this complex amplitude and quantify energy by limiting the absolute value of x and the absolute value of y to 0 or 1 to get the first two binary mechanics equations. M equals 0 or 1 and L equals 0 or 1. When M or L equals 1, it's called a one state or a quanta of energy in binary mechanics. So we have two kinds of energy, M and L. With length quantized in the italic L shown in the graph, a spatial object may be defined called the spot unit, where this energy occurs, called the M and L loci. Three-spot units in the lower right may be combined in our 3D space to form a spot. There are 8 permutations of the parts of the complex amplitude, shown in the upper left, which define a spot cube which predicts 8 elementary particles, 3 down or d quarks, and the electron, and their antiparticles. Finally, space is seen as a lattice or lattice of these spot cubes. With that short introductory background, we're ready to create a universe. Let's go, let's do this. Okay, step one in building our universe is that we need a place to put things. That place is the spot unit. 2, the spot unit is more than a volume to put things. What things do we have? We have the L and M type quanta, which represent units of energy. The spot unit must contain parts needed to implement the time evolution laws, which are equations 7 through 17 in binary mechanics. These parts might include guides, valves, and sensors. The guides, for example, a solid wall shown here in white would prevent motion of quanta through that wall. A valve, the red, orange, and yellow, allow passage of quanta in only one direction. Sensors are needed to sense the neighboring quanta for the scalar, electrostatic, and the vector or magnetic operations in the time evolution laws. The 8 elementary particles in the spot cube consist of 4 types or variations of these parts in spot units. 2 of them relate to matter, and these 2, the positron and the left-handed d quarks, are composed of this kind of pattern of parts in the spot unit. Point 3, intrinsic angular momentum. There was the 2011 discovery of the proton and electron bit cycles. The electron bit cycle is shown in the purple circle here, where one-state quanta in the electron spot revolve around the 3 spot units and return to the initial position, and that's the intrinsic angular momentum of the electron. The gray dot here is the axis of rotation. The proton bit cycle is shown by this larger arrow in this simplified version. 4, detailed account of motion mechanisms provides frame-by-frame steps involved in all particle motion. To build our universe, we need to know how particles move. An important discovery was the proton bit cycle, shown schematically by this larger circle, which rotates around the same axis in the center, which connects the electron spot with the positron spot on the other side. That the direction of rotation this intrinsic angular momentum in the universe and in proton particles is opposite to the direction of angular momentum for the electron particle, an important discovery. To make our universe interesting, we need a lot of complexity and variability. Thus, the electron has 2 to the 6 power states. There are 6 quanta locations in the electron spot, and each one of those could be in a 1 or a 0 state. Thus, there are 2 to the 6, which is 64 different configurations of the electron. That gives us a little bit of complexity and variability, doesn't it? Now, the proton, which is one of the hadron class of particles, has 2 to the 42 states. Here is the pro version of the proton bit cycle. There are 42 locations shown here in more or less the same angle of the schematic spot cube I showed before, where the dark red is in the upper left, the dark blue in the upper right, and the dark green is at the bottom. Notice that there are 3 areas here, one to the lower left, one at the top, and one at the lower right, which contain 4 quanta locations each, which are outside the main spot cube of the proton bit cycle. This allows energy in the proton bit cycle to venture into neighboring spot cubes, which is a very important point in nucleogenesis, as we're going to see. With knowledge of how things move, the motion mechanism, which, by the way, some recent videos have discussed in detail, we can add a new law of motion to the universe. Namely, objects move toward higher energy density. Let's denote a displacement or motion with dx, and note that we may have a higher energy density, which is a greater concentration or a greater percent of the loci in the one state, or a lower density area, fewer one state quanta in the volume, separated by a diameter d. Thus, we can let the energy density gradient equal d1 minus d2 divided by the diameter or size of the object. Now, this motion law applies at all scales. This could be a single proton. This could be a whole planet or a whole galaxy, our object here. Thus, we can say with displacement dx of one quanta in area A, our motion law force is going to equal dx times A times our energy density gradient. 8. The motion law acts to aggregate quanta into spatially separated objects. This aggregation effect occurs at all scales, from single electrons, protons, atoms, and molecules to solar systems and galaxies. To illustrate this idea, the figure below shows 2 spatial dimensions, and mountain height represents quanta density. Our 2 spatial dimensions are left, right, and near, far. The red arrows show quanta aggregation direction. So let's look at these 2 red arrows in the upper right of our illustration. Here we have quanta moving by the motion law toward areas of higher energy density. Likewise, we have particles or whole galaxies moving toward this peak of higher energy density. Notice that in this area here, we're going to have a lower density. Thus, we see in the universe that we have a sort of grouping of galaxies and vast regions populated with fewer galaxies. But we have a potential problem here. Through the action of the motion law, eventually everything in the universe is going to come together into one giant mass of energy. How do we solve that? Okay, extreme energy aggregation due to the motion law results in massive jets of quanta, which astronomers have observed, and explosions, such as supernovas, in volumes with near maximum energy density. let's look at some results from the Binary Mechanics Lab simulation software, which is a free download, by the way. The bottom here shows initial density for a simulation. We can start with very few quanta on the left here in our simulation, or have a whole lot of quanta, including up to maximum energy density. When we let the simulator run in a certain, what I call vacuum mode, all the quanta that leave the simulation are lost to the simulation. They're just gone. What is happening is that these quanta represent electromagnetic radiation and kinetic energy of particles in the simulated volume. And they can leave and go. And when that happens, the temperature of the simulated volume is reduced. When the temperature is reduced to 0 Kelvin, how do we know that, by the way? We know that because for a period of time running the simulator, no further quanta exit the simulated volume. There's nothing left to exit. What remains, and it's at 0 Kelvin. This is a very important point. So let's look at what we have here. This curve shows the final density, including both particles and so-called perfect vacuum. Perfect vacuum is just defined as there are no ions or atoms left in the volume. If we subtract out the particle part, we're left with the vacuum. And what this study shows right here is that vacuum is not empty, that it is full with quanta. In fact, most of the energy in the simulation at 0 Kelvin is not particles, but is one-state quanta circling in bit cycles for the proton and the electron, but below the threshold for creating a particle. You need a certain number of quanta in the elementary particle locations I showed you in the spot cube in order to have a particle detectable by our instruments. Now look at this point over here. At maximum density, when that is finally cooled down, you get a very low final density over here. This is a massive explosion. That's what that represents. Supernovas may produce low density volumes. And by the way, these volumes, very interesting point here about our universe, are opaque to light transmission. Why would this happen? Any incoming quanta to these low density regions or volumes would be captured in electron and proton bit cycles before any of that energy can make its way through that volume to be then seen or detected on the other side. So that's a unique prediction of binary mechanics. So we have a balance then between the energy aggregation due to the motion law and various explosions or massive jets of quanta leaving a highly energy dense area to balance it all out in our universe. So we're well on the way to making a pretty good universe here.